Today we're getting out of the water side systems and we're going to come back into an air side system in talking about energy recovery. So I've said this many times. Anytime we're bringing in outside air for ventilation purposes, if you're bringing that into your building, that takes a lot of energy to do. And I've said that tons of times. So I'm hoping none of you are shocked by that news. If it's 0 degrees outside, we need to heat that air up to 70 to 75 degrees before delivering it into the building. It takes a lot of energy to do that. Or in the flip side, in the summer, if it's a nice hot 100-degree day, now we have to cool down that air to 70 to 75 degrees before sending that into the building. And our commercial buildings, they can be either ventilation needs driven or exhaust needs driven. So what do I mean by that? If we have a ventilation driven system, that means the occupancy of the space or of the building, if you're looking at the building holistically, the occupancy of the space based on the number of people and the type of space, that's what's driving how much outside air we need to bring in. So a classroom is going to have different ventilation needs than an office space. A classroom is not only more densely occupied, there's just flat out more people in a classroom, but the ventilation rate in CFM is going to be higher per person for a classroom as opposed to an office. And for every CFM of outside air that we're bringing into the building, we also need to exhaust the same amount of air, of indoor air, to keep the building in balance. Because if we don't do that, we're going to end up over pressurizing the building. And that's when you have issues where you start blowing doors open. Sometimes if you have a pressurized building and a door is closed and it's pretty tightly closed, sealed up pretty well, but as soon as you go to open that door, it'll swing open really hard because now you've just given this air a path to go, and we don't want that to happen. Or conversely, you don't want to open a door and have it slam you right in the nose. So that would be a ventilation driven system. An exhaust driven system is based on the use of the space and how much exhaust air we have to take out of it. Some examples would be laboratories. If you have those fume hoods that are exhausting all kinds of air, if you're working with chemicals and things like that, or if you have a locker room, you want to remove those odors, or a large restroom, same thing. You're trying to remove the restroom odors, or you could have a maintenance garage. We looked at that Spokane Transit Authority building that McKinstry worked on a couple weeks back, and that would be an example of an exhaust driven system, because in that system we had to exhaust I think it was 0.75 CFM per square foot of garage. And again, if we are exhausting air, now we need to bring the same CFM of outside air in to keep the building in balance and to prevent negatively pressurizing your buildings. And then you can have the opposite problem where your doors start to swing inward. But in both of these scenarios, whether it's ventilation driven or exhaust driven, you can see how outside air and exhaust CFM, they're linked together. If you have a lot of exhaust, you need a lot of ventilation, and vice versa. So that brings us to energy recovery. What an energy recovery system does is it takes heat energy out of your exhaust air that you're dumping outside and uses that energy to precondition your outside air as it comes into your building. And this will have a drastic reduction on that energy intensiveness of treating that outside air that I've mentioned so many times. These are commonly used in what are called direct outside air systems, which is abbreviated DOAS. But in industry, we call that a DOAS system, which sounds a little funny the first time you hear it, but now I'm so desensitized to it, it just sounds like a normal word to me. So, what a DOAS is, it's essentially a large air handling unit, or I guess it could be a small air handling unit as well. No reason it has to be large. And it's going to provide pre treated ventilation air to lots of smaller HVAC units or direct into individual spaces. And the big difference here is a DOAS system is not providing the primary heating and cooling to a space. That'll be done by a separate system, and I'll have a visual to kind of show what that looks like. If you have energy recovery in a DOAS unit, they usually call that an energy recovery ventilator or ERV. But a DOAS system does not necessarily need to have energy recovery. It's just very commonly done. If you had a very small DOAS unit that was maybe a couple hundred CFM, that probably wouldn't warrant an energy recovery system on it. You still could, but if you had a 10,000 CFM DOAS unit, then that would have a very large benefit to having energy recovery. And actually, by code, you might have to provide that. They would make you put it on there just because it makes so much sense and would save so much energy. And the purpose of this DOAS is to what we call decouple the ventilation air from the main heating and cooling equipment. If you think back to the basic air handling unit schematic that we've looked at several times, I've always shown the outside air coming into the unit and then mixing before it gets delivered out the supply end. That would be more of a classic HVAC setup. What a DOAS system is doing now is taking the ventilation piece out of that and making it its own separate system. And the reason they do that is this allows those systems to run independently. We always need to provide ventilation air in commercial buildings. Whenever that building is occupied, we have to provide that. That's a code requirement. However, heating and cooling is not always needed. If you have a really mild day where it's, say, 60 degrees outside, maybe you don't need heating or cooling, but you still need ventilation air. And in that scenario, you only have to run the DOAS unit. You don't have to run this big supply fan that's on your main air handler. So what does that look like? Here's a extremely basic schematic for a DOAS system, specifically an ERV. So we have our ERV up on the roof, and you can see that our outdoor air coming into this thing and getting sent out to the space as ventilation air. And then this is also exhausting air from the space. And those air streams actually cross in this heat exchanger. And that means that the cold outside air coming in can actually steal some of that heat energy from the warm exhaust side of this. And now we don't have to dump 0-degree air into the space. And then we also have our main heating and cooling equipment. So we have our outdoor heat pump and our indoor fan coil. But you can see that that part of the system, which is going to provide our heating and our cooling to the space, is completely separate. There's no connectivity between the heating and cooling system and the ERV. And so now they're not dependent on each other to run. They can run as separate systems. And this is extremely simplified. This would be a one zone ERV with a single heating and cooling unit. typically the way this works is that DOAS would be ducted across a building and hit all kinds of zones. So you'd have a whole mess of ductwork where going to every single room, you'd have a ventilation supply and an exhaust that would all tie back into a common DOAS unit. Or maybe across your building, you might have 3 or 4 of these. When we're talking about how good our heat recovery is, that is measured by what's called effectiveness. And the effectiveness of a heat recovery system, it's an expression of the ability to recover recover the heat energy in the exhaust stream on a scale from 0 to 100%. So if our exhaust air that we are dumping outside, which is warm air that came from the building, if that's at 70 degrees, the most ideal scenario is we can take all of that heat energy out of it and put it into our outside air stream and heat our outside air up to 70 degrees. But that's an ideal scenario. Obviously, that's not going to happen. So we have to think back to this idea of approach, which has come up multiple times now over the course. That's the ideal scenario. Well, how close can we get to that? So here's a very simple example. In this case, we have an energy recovery device. This top stream here, running left to right, is our outside air stream. So it's coming in at a cold 5 degrees Fahrenheit. The exhaust side is on the bottom, coming in at a warm 70 degrees. We have an energy recovery device between the air streams to pull some of the energy from the exhaust side and put it into the outside air side. And we're getting that air up to 40 degrees. So we're pre-treating 5-degree incoming outside air with 70-degree exhaust air. So running through our problem statement, our outside air stream is coming in at 5, leaving at 40. Our exhaust air stream is coming in at 70. We could figure out what this leaving exhaust airstream would be, but at the end of the day, it really doesn't matter. And I'll explain why here in a second. So this energy recovery system is trying to extract as much energy from the exhaust stream as it possibly can. If hypothetically, our outside air came in at 5 and then left at 5, our effectiveness would be 0%. We didn't gain anything out of this heat recovery device. But if hypothetically our outside air comes in at 5 and leaves at 70, which is the same temperature as our exhaust, that would be the ideal scenario, and our effectiveness would be 100%. But we're somewhere in the middle. We're coming out at 40 degrees Fahrenheit. So what is the effectiveness from 0 to 100%? It's a pretty easy calculation. So the effectiveness is based on our outside air temp leaving the energy recovery device minus the outside air temperature entering the device. So you could see that as that is our actual performance. Temperature leaving minus temperature entering. How much delta T did we actually get out of this thing? And then we divide by what is our exhaust air temperature entering the device minus our entering outside air temperature. And you could look at that as this is our maximum delta T we could possibly see. Because if this exhaust air temperature entering the device, that's as good as we could get in an ideal scenario. So this bottom term, that's the maximum delta T we could see. And so if we calculate that in this example, 40 minus 5 divided by 70 minus 5, we have an effectiveness of 0.54, i.e. we recovered 54%. And you can see by looking at these terms, if our leaving outside air temperature right here were to increase, it would start to approach this 70 and result in a higher effectiveness because we're recovering more energy out of the exhaust stream. You can also see the leaving air coming out of the exhaust side doesn't really play into this equation. If these two air streams have the same airflow, which they usually do, but not always, let's say both air streams are 2000 CFM, the delta T on the outside air side will equal the delta T on the exhaust. It has to, just by the laws of thermodynamics. So if we were to see a 35-degree rise on the outside air, we'd see a 35-degree drop on the exhaust air. But as far as our calculation here, this term just doesn't come into play. The energy recovery technology might differ. The way you recover this energy can be different, but this effectiveness calculation is going to be the same no matter what. So let's get into those technologies. First one is what's called a pumped runaround coil. You're going to have usually 2 coils. You could have more than that, but most commonly it's probably just 2 coils. And these coils are constructed just like hot water and chilled water coils. And you'll have 1 coil in an exhaust airstream and 1 in an outside airstream. And then you just pump water between those 2 coils. So you pump water to 1 coil, which then goes to the other coil and just goes back and forth. So in our exhaust airstream, the water that's running through the coils is going to heat up because that's where our warm air is. And that's going to pull energy out of the exhaust air. And then in the outside airstream, this water, now that it's warm, is going to go into your cold outside airstream and preheat the outside air. This is what this looks like. So we have our outside air coil. You can see it's coming in cold, leaving warm. We have our exhaust air coil coming in warm, leaving cold. We have our pump to move water between the coils. And let's say our outside air coming in is 32 degrees. Our exhaust air in is at 72. And we're going to send cold water, say 39 degrees. This is all just hypothetical for this example. If we send 39-degree water into this coil, that will cool down our exhaust air, and say that comes out at 45. Since the water came in cold, it picked up heat energy, then it's going to leave warmer. So let's say that comes out at 66. So now we're sending 66-degree water into this coil where it can get rid of that heat, and our outside air out comes out at a warmer temperature. And you just keep running that pump and just keep moving that water, and you'll just keep recovering that energy. The pros of this type of system is primarily you're able to tie together systems that aren't even close to each other. So you could have your outside air ductwork in one location, and maybe your exhaust air is 100 feet away. Well, you can run 100 feet of pipe and still connect those systems and recover that energy. It's usually a good option if your exhaust and outside air is centralized between 1 or 2 units. I mentioned most often it's a 1-to-1 basis where you'll have 1 intake and 1 exhaust, but you could have a scenario where maybe you have 1 outside air, but you have 3 exhaust fans throughout your buildings. And you could pipe this to multiple coils and pick up energy at each one. And that's not a huge deal as long as it's just a small handful. Some downsides: it's not the most effective recovery technology. So it's around 45 to 50%, which is okay. It's certainly better than nothing. But compared to some of the other technologies we're going to talk about, this isn't the best. And it's not as useful if these airstreams are broken up among many pieces of equipment. For example, that Spokane Transit Authority maintenance garage project that we looked at, we had, um, guessing here, let's say 10 outside air supply units and probably 16 exhaust fans. So that would not be a good candidate for a pumped runaround system, because we would need one of these at every single one of those units. So that would be, over 25 coils. That would be a very big system. That'd be very expensive. You're also adding some maintenance requirements. Now the owner that you've put this on, they have to worry about that pump. That's one more device they have to worry about failing. And one potential downside is if that pump fails, maybe the system is not sized to handle the heating load without that recovery device on there. If that pump goes down, now you have to fully condition this outside air, and maybe the system just can't handle that. Next up, we have what's called an energy wheel. In an energy wheel, you have your exhaust and your outside air ducted either on top of each other or side by side. Either way, they have to be running right next to each other. The reason being, you're going to have this wheel that's going to turn between these two airstreams. And that wheel just happens to be made up of a material that is very good at picking up heat and discharging heat. So the wheel is going to warm up as it turns through the exhaust airstream. And then as it gets into the outside airstream, then it will reject that heat energy that it picked up. And the wheel just keeps spinning. Like most things in HVAC, it's just a cycle, just goes on all day. So this is what that wheel would look like. So we have our outside air coming in at a cold 7 degrees, and we have our wheel spinning between our outside airstream on top and our exhaust air on the bottom. And so this wheel just turns and turns, picks up heat energy on this side, and then as it turns into the outside air, then it'll pick up that heat energy and heat it up. So you can see why the airstreams have to be right next to each other. That's the only way this configuration is going to work. The pros of an energy wheel: it's pretty effective. Compared to a pumped runaround system, 70 to 80%, that's pretty good compared to 45 to 50%. And you can buy these wheels integral to your air handling units. It's just something that you purchase the unit with. You work with a manufacturer and you say, this is the size of unit I need, and I need it to have energy recovery. So you can just buy it completely integral and basically just ready to go. The downsides, though, is the two airstreams, they have to be part of the same unit, or at least have to be ducted next to each other. And your two airstreams will have some slight cross-contamination. The two airstreams, where they meet, where that wheel sits, that is not by any means a perfect seal. And so you will get, I want to say it's 1 to 2% of a cross contamination where you will actually pull some of the exhaust air back into the outside airstream. In a normal application or a typical application, say for a classroom or an office, that's no big deal. So what? We recirculated 1% of our air, whatever. But if it's a lab environment where you are working with chemicals and things like that, that is a very big deal. There cannot be any cross contamination in a system like that. And this does add some maintenance. The the wheel itself has a motor in order to turn the wheel, and you need to make sure that you periodically clean your wheel. Normally what they do is they do put filters just before the air hits the wheel on both sides of the unit, on the outside air and the exhaust air. But the filters don't quite catch everything. And so periodically, you have to pull that wheel out and hose it down to get it clean. And then with the wheel motor itself, similar to the pumped runaround coil, if that motor fails, now you've lost your energy recovery, and maybe your unit is not sized properly when that energy recovery is not doing its job. And that's actually a code requirement in Washington where they say you have to size your equipment assuming your energy recovery systems are doing their job. Because what they don't want to happen is for the energy recovery device to fail and then for the owner to just say, well, I'm just not going to fix it. I'm just going to run my other heating systems harder. That's what they don't want to happen. They want to encourage you to fix your energy recovery because they save so much energy. Last up, we have what's called a fixed plate heat exchanger. Similar to a wheel, we have our exhaust and our outside air ducted on top or side by side of each other. They have to be right next to each other. And both of our air streams are going to cross over each other, not necessarily mix, but they're going to cross through a cross flow heat exchanger. Within that heat exchanger, we have a lot of these interlocked, very, very thin metal plates that are going to transfer heat energy between our two airstreams. So here's a fixed plate heat exchanger. So we have our cold, fresh air coming into the unit, going through our energy recovery core, is usually what they call these. We have our stale, warm air from the building coming in, crossing through the same heat exchanger. And as those air streams cross, they transfer heat energy. We end up with warm, fresh air on one side and cold exhaust air on the other. And this image here shows how these plates are interlocked. So like I said, these air streams are not mixing together. We don't want to do that because that would dilute the ventilation air that we're trying to send into the building. But you can see the outside air, these little triangles, they alternate from side to side. So every other plate is outside air and then return air and then outside air. And that gives you really good heat transfer between your two airstreams. And here's one that I spec'd on many jobs, and this shows what it looks like. Actually, if you think back to when we talked about Tico Elementary, I had some photos of one of these out in the wild. But we have our two supply fans. So that's what's moving our air. One would be for the outside airstream, and one would be for the exhaust air. You can see the motor tucked away back there with a belt to drive our fan impeller and the fan casing right there. We have our heat exchanger core there in the center. And you can see we have filters here as well. So they put the filters right before the air goes into the recovery core, just to make sure they're protecting the core, trying not to get it dirty. Although, like a wheel, you still over time might have to pull this thing out and hose it down. It's a little harder to do with these big recovery cores than it is a wheel, but it can be done. The pros of this kind of system, they're also fairly effective. Not quite as effective as an energy wheel, but they're competitive with them. Most of the ones I've spec'd are between 70 and 75%, which is still quite a bit better than a pumped runaround system. Similar to a wheel, you can buy this all integral to the air handling unit and just get it all packaged and ready to go, so you don't have to put a bunch of parts together in the field. It's pretty simple. There aren't really any extra moving parts. This heat exchanger is a passive device. We don't have any motors that we need to turn wheels or pumps to move water. So it's comparatively a very simple system that isn't going to just randomly fail because your wheel motor just happened to give out on you one day. And there's no cross contamination, which is going to be really good for a lab or other type of environment where you just absolutely cannot have that cross contamination. The downsides, though, just like a wheel, our two airstreams have to be part of the same unit for this to work. That's the only way this is going to work. Generally, they also have a bit higher cost compared to some of the other technologies. So with energy recovery, we're getting into interactive effects here. For any of these technologies, we're placing another heat exchange device in our airstream. And anytime we put something in the path of the airstream, we are adding static pressure requirements. By putting a wheel or a heat exchanger or a pumped runaround coil in that airstream, that is adding resistance to that air movement, which means our fan is going to have higher static pressure requirements. And so, if we are adding energy recovery, we are ultimately going to add some fan energy that wasn't there before. If you think back to our fan horsepower equation, CFM times total static pressure divided by 6,356 times the product of our efficiencies, we are increasing that value, our total static pressure requirement, by adding a recovery device. And if we know what that pressure drop is that we're adding, we can now estimate what that added fan horsepower is going to be. As an example, let's say we have an existing fan system sized for 5,000 CFM at 2.5 inches water column of total static pressure with a 70% fan efficiency and an 88% motor efficiency. So we can use that to figure out a fan horsepower. And let's say we want to add an energy recovery device to this fan that'll add 0.75 inches of water column of static pressure. If we calculated our base horsepower just by running through the calculation that you should be pretty familiar with at this point, so we would have an operating horsepower of 3.19. And then our proposed horsepower would be the same equation. We've just increased the static pressure, and that would result in 4.15 horsepower. So our added horsepower would be 0.96, An alternative way to look at this, if you were only concerned about that delta, you can just run through the formula and just plug in the added static pressure. Just plug in 0.75 in your numerator and you'll get the same answer. If you have a pumped runaround system, so now you have a recovery system that requires a pump. And that pump was not there before, which means there wasn't a pump there using energy before. So this will add energy to your system whenever the pump is running during energy recovery. And this is on top of this added fan energy due to the pumped runaround coils that we've stuck in those airstreams. So we have two sources of an energy use increase, added fan energy and added pump energy. If you have an energy wheel, then you're going to have to turn this wheel motor. And that wasn't there before either. So that's going to add some energy just to turn that wheel. Again, in addition to the fan energy that wheel has just because we stuck that in the airstream. Just like the pumped runaround coil, except for the wheel. So inherently, with any energy recovery system, there's a trade-off between the energy you're going to save through your recovery and some energy increase due to added fan or pump energy. There's going to be a trade-off. Energy saved plus a little bit of a hit. And there might be some conditions, some moderate temperature conditions, where that penalty you're paying to run that pump or to run air through that coil is going to outweigh whatever benefits you might see. Because if you think about it, the energy required to run that pump in a pumped runaround system, that's a constant penalty. That pump is running and drawing the same amount of energy regardless of outside air temperature. But your benefit is going to change as it gets more moderate outside. So you might see very good benefits when it's very, very cold, where the benefits far outweigh this added pump energy. But then we get this 50-degree day where that pump energy is going to offset all of that recovery that we're trying to achieve. So far today, we've been talking about energy recovery in context of a heating system, assuming that we're taking in cold outside air and then pre-treating it. But these technologies, all of them, we can also do the same thing when we're in cooling mode. And instead of heating up cold outside air, we're going to cool down hot outside air. But energy recovery is not as useful in the summer due to a couple reasons. Reason one, we have a much lower delta T between our summer outside air and our indoor space temperatures. Using Spokane as an example, a design day in Spokane would be around 100 degrees outside, and we maintain our buildings at around 75 degrees. So that's a 25-degree temperature difference that we're trying to achieve in getting that outside air temperature to a comfortable point. In comparison, our winter days at design days around 0 degrees. And we keep our buildings at around 70 degrees in the winter. So that is a 70-degree temperature difference. And the greater the delta T, the more recovery opportunity there is. So that's reason one. Second reason is cooling processes usually have better efficiencies than most heating processes. DX cooling systems usually have a COP of about 3 to 4, whereas a gas heating system is 0.8 to 0.9, or 1.0 if you have electric resistance heating. If you have a heat pump, It could be better, but generally speaking, cooling processes have better efficiencies. So not only is our delta T here not as drastic, but the energy it'll take to get from 100 down to 75 is not going to be as substantial because our COP is so much better. It's still beneficial to do it in cooling mode, but the energy savings on that side are just not as apparent. If you already have the energy recovery device installed for heating mode, there's no real reason to not also do it for cooling mode. But it would be a rare occasion that you would install an energy recovery device only for cooling. Say if you were in Arizona or Florida, where it's pretty much cooling mode year round, you probably wouldn't install an ERV just for cooling. There might be some examples. So, could depend on the specific climate, but generally speaking, most of the benefit here is on the heating side. So, when does it make sense to use energy recovery? I already kind of touched on this at the beginning, but if you have any system that requires a lot of outside air or a lot of exhaust air, then that system could benefit from an energy recovery system. If you have large outside airflow requirements, that means you have to have large exhaust airflow requirements, and vice versa. Those two things are intrinsically linked. So if you have kitchens, paint booths, schools, I mentioned earlier, schools tend to have a higher ventilation requirement just by nature of the type of facility it is and the higher occupancy rates, or labs, although be careful of cross contamination. So, some pitfalls, some things to watch out for. If you're putting on an energy recovery device on an existing air handler, you're adding pressure drop to the existing fan. We already talked about that, and we talked about the energy impact, but also, at best, you're going to have to adjust that fan, and you're going to have to do what's called a rebalancing. Normally, when you do a construction project, you buy all the fans you need, and then you have to hire a balancer who goes out there and makes sure all of the fans on that system are moving the amount of air they're supposed to. So if you go in after the fact, put in this new energy recovery device on an existing fan, if the fan's not adjusted, then you're going to reduce the total airflow because you're adding resistance to the system. And if you don't rebalance the fan, that will result in less airflow. So that's best case condition. Worst case condition, you might have to replace the fan or the fan motor. In that previous example, where we were adding 0.75 inches of water column to an existing fan, what if that fan or that motor doesn't have the excess capacity to handle that extra 3/4 of an inch? That means you have to replace the fan or the motor. Maybe you have to go from a 3 horsepower motor to a 5 horsepower motor. And if you are upsizing your fan motor, say from a 10 horse to a 15 horse, well, now there's electrical considerations. Now you can't just feed that motor with the same conductors that you were feeding it before. And so this can sort of spiral a little bit. You think it's so simple to add this coil, makes so much sense, but if you didn't do your due diligence to make sure that the fan and motor can handle it, this could turn into a much more expensive project. If you're doing retrofits on existing equipment, pumped runaround is the most common because it's the most flexible and it's often the lowest cost. The reason it's the most flexible is your outside and exhaust airstreams don't need to be close to each other. It's the only option we've talked about where your two airstreams can be separated by hundreds of feet. Or you could have multiple outside air and exhaust points and have multiple coils to do that. If you're going with a pumped runaround system, that requires the least amount of ductwork modifications, which if you're doing retrofits on existing equipment, that can be a big deal. You can keep all of the ductwork in the same place and just install these new coils. Just put those coils wherever you need them. Typically, we're only going to see energy wheels and fixed plate heat exchangers when we're replacing entire units or if we're doing new construction. Uh, Or I guess if we were doing a significant renovation where we're getting and replacing the entire HVAC system, that would be a case where you would see energy wheels and fixed plate heat exchangers because we're able to order the new equipment with our recovery integral to the units, but you might have to reconfigure the existing ductwork to make this work. And that could be very expensive. So we've talked about the most common heat recovery methods, a couple other ones worth briefly talking about that are much less common, but you might find kind of interesting. There's one called a heat pipe, which is a little unique because there's no mechanical components and no input energy required. So this is kind of a set and forget kind of device. And what this does is it uses refrigerant as your heat transfer medium between your two airstreams, but there is no compressor. One of the few systems that uses refrigerant but does not use a compressor to achieve its heat transfer. So you can see this sits at an angle. I didn't just rotate this image. This is how it has to sit. And you're going to have your cold airstream on one side and your warm airstream on the other. And what happens is the refrigerant that's in this pipe, it's going to absorb energy on one end and then naturally just want to rise. So I said there's a reason this is at an angle. It's going to want to rise towards the top where, and then it'll discharge its heat energy and then it'll naturally want to fall. So this is going to cause a phase change of the refrigerant as it just moves from the high point to the low point. It's going to just discharge heat and then absorb heat just over and over again, but it doesn't need a compressor to do that. It's just using the natural buoyancy of the refrigerant as it changes from a liquid to a gas. I've always heard about these, but I've never actually spec'd one on a job. I hear they're very expensive, so I'm not entirely sure when this would be warranted. And then last up, we have what's called a plate and frame heat exchanger. The idea here, and this is kind of an exploded view a little bit, you have a number of these flat plates that are bundled and sort of sandwiched together. And in these plates, we're going to alternate between our hot and our cold streams. And this would be a water-based system. So we can see, in this case, we're sending in steam as our hot product. And then we're sending in some unnamed other fluid in on the cold side. And the cold side is going to heat up as it goes through these plates and then come out the other side warmer. So this would only be used in water to water heat transfer applications. It's not super common to use this as an energy recovery device. It could be used, and I'm sure it is in some special applications. For example, I know for large brewers, beer brewers, they use heat recovery because they they reject a lot of heated water that is just getting dumped outside. And at some point, somebody had the bright idea that, hey, that's a lot of energy we're just dumping down the drain. I wonder if we could use that to preheat some other water source that we're using at the start of our beer process. And now virtually every brewer, big brewer, has heat transfer devices to do that. But in commercial applications, we don't see it very often. But it is used all the time as a general heat transfer device. And that's all I got for you. Any questions? All right. I'll stick around for 15 minutes or so for homework questions. Otherwise, have a good weekend, and I will send out an email regarding the final exam just as a reminder that I need to know if anybody takes issue with taking that on Monday. So have a good weekend.